So in this video, we're going to do an example of calculating the pH of a salt solution. And for our example, we're going to use sodium benzoate. There's the formula, which is used as a food preservative in things like salad dressings because it inhibits the growth of bacteria and fungi. The pKa of benzoic acid, the conjugate acid, is 4.20. So predict, will a solution of C6H5CO2Na, sodium benzoate, will that be acidic, basic, or neutral? A solution of sodium benzoate is expected to be basic. So in water, the C6H5CO2 will dissociate from the Na+. And so the Na+ is a neutral ion because it is the conjugate acid of a strong base, so it has no effect on the pH of the solution. Whereas C6H5CO2, it has a minus charge. It can accept a proton to form C6H5CO2, which makes it a weak base. So benzoate ion is going to be a weak base. It's the anion, so it can accept a proton, which is what makes it a base. It's not one of our strong bases, so we know it's a weak base. So that's going to make our solution basic. Okay, given that we know that the benzoate ion is a weak base, let's write the balanced reaction, the chemical equation, for the reaction of benzoate in water. All right, so to start with our reactions, we're going to take C6H5CO2 minus, and we said we're going to react with water. All right, if benzoate is a weak base, we know we're going to produce OH minus. And then what's left over is the benzoate ion plus an H plus. And so the H plus and the minus, those charges are going to cancel, and we're just going to add the H here on the end. And so this compound is benzoic acid, the conjugate acid of benzoate ion. And so we see that this reaction is written as a weak base plus water produces hydroxide and the conjugate acid, which means that the equilibrium constant for this is going to be a Kb. Now, if we have a solution of sodium benzoate, what would we expect the pH of that solution to be? So a reasonable concentration for this might be something like 0.0069 molar, which represent a 1.1% solution in water by weight, which is the FDA limit. Now, probably you're not adding benzoate as a preservative for your water, but if you were, this is what it would be like. Okay, so our goal is to calculate the pH of a 0.0069 molar solution of sodium benzoate. We've determined in the previous slides that the important reaction here that affects the pH is going to be this benzoate Kb reaction. So C6H5CO2 minus plus water goes to the OH minus plus the conjugate acid C6H5COH, CO2H. And that this is going to be, the equilibrium constant can be represented by Kb. So now we want to know the pH of the solution at equilibrium. So we're going to set up our ice table. We know that the initial concentration of benzoate is 0.0069, the same as the concentration of sodium benzoate, because there's one benzoate ion for every mole of sodium benzoate. We know that water doesn't matter because it's a pure liquid, that the initial concentration of hydroxide in water is basically 0, and that there won't be any benzoic acid until after the reaction happens. We know this reaction will go toward the products, and that we can set up our Kb expression using these amounts that we calculate for equilibrium. So Kb will equal x squared over 0.0069 minus x. Now, what's the value of Kb? We aren't given the value of Kb. We're given the pKa of benzoic acid. So we're given the Ka, the pKa, of the conjugate acid. We can use the relationship with Kw, that Kw equals Ka times Kb to figure out the value of Kb. We further know that, so if we have pKa, that's going to be negative log of the Ka value. So to get rid of the p, we're going to take both sides to 10 to the negative power. So 10 to the negative pKa equals Ka. So to find Kb, we've got Kw, which is 10 to the minus 14, divided by 10 to the minus 4.20, the pKa. So we find that Kb for benzoate ion is 1.59 times 10 to the minus 10. Okay, so I'm going to continue. We're going to take this expression down here to a new space. So Kb, we said, equals x squared divided by 0.0069 minus x, and that is equal to 1.59 times 10 to the minus 10. Now, given how small Kb is here, it's going to be pretty safe to make the small x approximation. And so we'll do that, and then we'll check and see if it works. So if we assume that 0.0069 minus x is about equal to 0.0069, then we see that x squared equals 0.0069 times Kb, 1.5 times 10 to the minus 10. And so that means that x equals 1.05 times 10 to the minus 6. And as we expected, our assumption is valid. So that x value equals the OH minus concentration. If we want to know the pH of the solution, we need to know the H3O plus concentration. We remember that the OH minus concentration equals Kw divided by the H3O plus concentration. Oops. And the more useful version of that would be that the H3O plus concentration equals Kw times the OH minus concentration. All right, so we can calculate H3O plus 10 to the minus 14, which is Kw, divided by our x, 1.05 times 10 to the minus 6, which gives us an H3O plus of 9.52 times 10 to the minus 9. And then if we calculate pH, sorry, this is becoming kind of a mess, we get that the pH is 8.02. 8.02, a slightly basic solution. And that makes sense because we have a fairly dilute solution, 6.9 times 10 to the minus 3rd molar, of a weak base, benzoate ion. And so our solution is slightly basic.